Okay, here's for the third and last part of last year's written exam. After this, I'm also going to be going through the computer lab exam, but that is a separate part. This last third here will be going through the part of the class that relates to metabolic modeling and flux balance analysis and all that. So our first question, which is a rather initial approach to FBA, is on the topic of the steady state assumption. And so the first part is, what is the premise of the steady state assumption? Basically, the steady state assumption states that metabolites are cannot deplete indefinitely or accumulate indefinitely. Essentially, that we have that since the cell is in a steady state, the net production of each metabolite, the net production of each metabolite, sum of consuming plus producing fluxes must be 0 over time. That is essentially what the steady state assumption says. And that, of course, will put constraints on the fluxes. Constrains fluxes through each reaction based on satisfying this requirement for all metabolites. That is the base premise of the steady state assumption. In addition to that, mass balance is another key assumption. Mass balance typically means that the outgoing metabolites from one reaction must be mass equivalent to the ingoing metabolites from a given reaction. So, for instance, if you split up 2H2O, you're gonna get whatever you get on the other side has to be if you take 2H2O in, then you can have 2H2 out and 1O2 out, right? That's mass balance. You can't have elements appearing out of nowhere, and they can't go into nowhere. But there is one type of reaction for which this mass balance requirement is typically not enforced. And what kind of reactions are that? Well, and why is that kind of exception necessary? Well, exception for mass balance. The exception for mass balance is exchange reactions. Typically, exchange reactions are phrased so that they can import or they can create a given metabolite from nothing. And this is necessary because if you're going to have growth and if you're going to have secretion, those things will leave your system and they have to go somewhere. If you're not going to allow anything to be created from nothing anywhere, then you're going to be stuck with a static system. So mass balance exchange reactions are allowed to be mass imbalanced in order to represent the import of metabolites into the system and to feed the internal fluxes. That is essentially the exception to mass balance, and then steady state and mass balance are sort of two requirements that actually feed into each other, that interplay quite significantly for FBA, because it's the combination of the two that really imposes the key set of constraints on from the stoichiometric matrix. Okay, so let's other than that, start off with a simple true-false on these 5 statements. And so it's simply taking which of these statements are true. So let's go through them one by one. The first is the stoichiometric matrix is the source of the inequality constraints in the FBA linear optimization problem. This is not true. The inequality constraints, so again, to recap, in the FBA linear optimization problem, we typically have 2 types of constraints. We have equality constraints and inequality constraints. Equality constraints we touched on in the previous question. They come from steady state and mass balance. And fundamentally, the stoichiometric matrix is a representation of the steady state problem. Essentially, that the stoichiometric matrix multiplied by the flux vector has to equal the null vector. That essentially is the mathematical representation of the steady state requirement. And so, but that that constraint is an equal type constraint. Essentially, that the stoichiometric matrix multiplied by the relevant fluxes has to equal 0 for each metabolite, but it has to equal. In addition to that, the inequality constraints, they come from the constraints on individual fluxes, typically exchange reactions. You'll also mathematically have, from a programming point of view or a code point of view, you're also going to have fixed inequality constraints on internal reactions, but these are typically set high enough as to be irrelevant. But the inequality constraints come from outside of the stoichiometric matrix. So this is not true. When making a genome-scale metabolic reconstruction, one must only include a reaction if there is direct genetic evidence for it. And this is also not true. While certainly direct genetic evidence is a very strong reason to include a gene, and definitely the inverse of this statement is true, that is that if you have genetic evidence for a reaction, that reaction should be included. But you will often have cases where, for instance, you're building a model and you want to gap fill. You start with your genome and you do your automated model reconstruction, and you'll end up with a sort of incomplete metabolic system which is not capable of carrying fluxes that it phenotypically should be able to do. And if you can sit down and look at the pathways, and you might see that maybe if only this one reaction here that we have no genetic direct genetic evidence for, if only this reaction was actually possible, then our cell or our model would behave much more like in reality. And there, even though you do not have direct genetic evidence for it, that would be a reasonably strong argument for including that reaction in your metabolic model. So, second statement is not true either. The third statement is, a MoMA optimization may have a unique solution that is not located on one of the vertices, corners of the feasible solution space, while any unique solution to a linear FBA problem must be located on a vertex. And so, when we look at the linear optimization problem, we can convert this into sort of a visual problem, at least in the simplified case where we only look at 2 or 3 dimensions, where the set of constraints impose a specific shape on a feasible flux space. And in addition to that, we will have an optimum function that, an objective function that we're trying to find the optimum of. And so, in a linear FBA problem, this is just like an abstract direction, right? It's a general. The objective function will always be a linear vector that goes straight in a given direction. And because of this, it's similar to, say, considering something in the direction of gravity. If you have something that is a convex polygon, which is similar to what you'll have, what the shape of the solution space will be, and you're orienting that however which way you want in space, and you consider that you have your gravity vector, which just points down. Of course, in real life, gravity vector points to a specific point, but on day-to-day scales, no matter how far you go, no matter how you orient yourself and what point you're at, all the gravity vectors are going to be parallel. Essentially, if you then rearrange your, no matter what the shape of your polygon is in space, if it has, there will be one point of it that is the bottommost, right? The one that has the lowest coordinate in the vertical axes. And you can either have a whole surface being the bottommost, where every point on that surface is equally has equally low z coordinates, or you can have a line, like an edge, that constitutes this lowest most point, or you can have a single point, or a single point is this lowest most point. But if the lowest most point of any polygon must be a corner, you can't have a single point on the surface being the lowest most. That just doesn't work. For MoMA, the main difference between MoMA and FBA in this context is the objective function. The feasible solution space is the same, but we're optimizing for something else. While in FBA, we're optimizing for a constant objective function, and essentially that the optimization vector, the direction of optimum, is uniform and constant and always points in the same direction. MoMA points towards a specific point. Essentially, we start with our pre-knockout optimal solution, and then once we perform our knockout or our change in environment or whatever we want, we will be reshaping the solution space, and we want to find the single point in that solution space which is the closest. And that means that the lines of equal objective function, they're going to form circles. And if we look at this, for instance, here, I'll actually pop up a little bit of an example to okay, this is not necessarily the best example, since this is a curved. No, never mind. If we ignore this curve C here, if we just look at the circle from the center here and this line, there will only be one point on this line which is the closest to the center of the circle, based on essentially how geometry works. And that means that, and since essentially a circle corresponds to a set of points that are equidistant from our original solution, any solution to an FBA problem, to a MoMA problem, any equivalent solution to that solution would also have to be on that circle. But again, based on geometry, the contact point between any such circle and our solution space is only going to be a point if that point is optimal. And so, to return to the question, a MoMA solution not only may have a unique solution that is not located on a vertex, it will have a unique solution that is not located on a vertex unless you are in a very fringe case. While any unique solution to a linear FBA problem must necessarily be located on a vertex. You can have solutions to an FBA problem that isn't on a vertex, but then it is not unique, is essentially the point. So this statement is true. For a given mutant strain, MoMA-based solutions normally show higher growth rates than the corresponding FBA-based optimal solution. And so again, when we're doing MoMA and FBA, typically not typically, like the solution space is going to be the same. The difference between MoMA and FBA is going to be, or for a given mutant, is going to be the objective function. And since in FBA we're optimizing for growth, whatever solution we find to FBA will necessarily be the highest base growth. While MoMA, the optimal solution for MoMA, is the one that is going to be the closest to the original, or to the unperturbed optimal solution. Which may be optimal in terms of growth, but may also not be. That is not a requirement, and in practice you'll often see that MoMA performs quite a bit below optimal growth. Essentially, since we're optimizing for growth, any solution, it's impossible to have a MoMA-based solution that shows higher growth rate than the FBA-based solution, because the FBA-based solution is optimizing for growth, so this statement is false. And our last statement, in FBA, an organism made incapable of growth by a single gene deletion may once again become viable with an appropriate second gene deletion. When we're deleting genes, essentially what we're doing is we're narrowing down the solution space. We're making it smaller. And what we're saying in FBA when a gene is or when a knockout is lethal, so if it's incapable of growing, that there is no point in that solution space which has a higher growth than whatever our cutoff for viability is. And since any second mutation is going to shrink that solution space even further, there's no way that you can then have the second solution space include any point where you have sufficient growth, because our second subspace after the second mutation, or our second solution space after the second mutation, is necessarily going to be smaller and entirely contained within the solution space we got after the first mutation. And if the solution space after the first mutation does not contain any point which is compatible with growth, then the second solution space necessarily mustn't either. So this statement is also false. Okay, on to the next question. Here we're asked about stoichiometric matrices. We're given a metabolic system with a set of 6 reactions, and we're asked to convert this into a stoichiometric matrix. Unfortunately, Inspera is a little bit of a pain, so we have to type in all the zeros, but we can do this. So, as specified here, rows correspond to metabolites, columns correspond to reactions. And so, if we look at reaction 1, metabolite A, that means that metabolite and metabolite A is on the right hand. So that will simply correspond to 1 here, and then for reaction, and the rest of column 1 is going to be 0. Reaction 2. Now this consumes 1A, so we're going to put -1. It produces 1R2, so that's going to be B. It produces 2B, so that's going to be the second line here. And then the rest goes 0. Reaction 3 takes 1A and produces 1C, so that goes on the third row. The rest are 0. Reaction 4 produces or consumes 1B, 1E, which is the 5th row here, and produces 1D. Reaction 5 exports E, so it's going to be 0 and everything except E, which is except 5, which is +1. And R6 only consumes D, so it's going to be -1 for the 4th row, and then and that is pretty much it. Okay, next topic is FVA. So the base principle of flux variability analysis is we want to find how flexible a flux is under optimal conditions. Essentially, for a given FVA solution, how much can the fluxes vary? Because as we've touched on earlier, and as we've discussed in class at length, any given solution to the FVA problem is not necessarily unique. It might be located on an edge or a surface or any higher dimensional object than that. And so it's often useful to try to chart which fluxes correspond to any sort of variability in optimal solutions. And so one way we can do that is through FVA. And so with FVA, what we do is first we compute an optimal solution for the FVA problem. We then set the optimal value of the objective as a constraint, and then we optimize, and then we go through all other reactions one by one and optimize two ways for that, for each reaction, which is minimize and maximize. This gives us an upper and a lower bound for that reaction given an optimal flux distribution. That is essentially how FVA works. Now the question is, why is this a naive approach to understanding possible flux distribution for a given growth rate? Well, this is because we only get the variability of reactions one by one. We only get bounds for each reaction in isolation. And what we can have is we can have two different reactions. Suppose we have two reactions with flux bounds V1 max, V1 min, V2 max, and V2 min. From FVA, which means that we're in the that all of these fluxes, so these are fluxes that are possible while being an optimal solution. Even though V1 can take any value between V1 min and V1 max, and the flux could still be optimal. This doesn't mean that you can simultaneously have V1 equals V1 min and V2 equals V2 min at the same time. Essentially, FVA only gives us a flux for possible values for a single reaction at a time. It doesn't really tell us the shape of this optimal solution in any sort of thoroughly concise, exhaustive way. And yeah, so that's FVA summarized. Okay, next aspect, and we're talking about the evaluation of reconstructions. So when we're doing a genome scale reconstruction, what we want is we want to build a model that represents the cell in real life. And specifically, we want three aspects of cell behavior that a genome scale reconstruction should be able to replicate. And of course, there are many different possible choices here, so I'm just going to say point out three that I feel are relevant. First is ability to replicate growth rate and secretion of metabolic byproducts. The model should predict similar rates as experimental values. Second, ability to grow on in various media. Essentially, in a model, what we can do is we can adjust its we can simulate a certain environment in a nutrient media by adjusting the uptake fluxes, or the bounds on the uptake fluxes in the model. And if we then say that, oh, this organism here in our model can grow anaerobically on lactate but not on succinate, this should also be something that is reflected experimentally. So the model should be able to grow in simulations of media where that correspond to media where the cell can grow experimentally and unable to grow and be unable to grow in media where real cells can't. And third, which is somewhat similar in qualitatively, but is done in a different way, is identify the model should respond appropriately to gene knockouts. Yeah, blocking reactions corresponding to experimentally essential genes should be lethal in the model, while deleting non-essential genes should leave the cell still viable. These are three different key aspects of cell behavior that we can consider that a good genome scale model should be able to replicate. Okay. Next on here, I think we have a metabolic system. I think it's the same as we had earlier. Yeah, pretty much. So the question is, here, which reactions are single essential for the production and secretion of metabolite D? I realize in retrospect this could actually have been a multiple choice, but so be it. So if we look here at metabolite D, it's secreted through R6, and it is produced by R4. So these two reactions are clearly essential on their own. Obviously, if R6 was knocked out, we first of all couldn't secrete D, and since we then couldn't secrete D, we also couldn't produce it, because then we would have an indefinite buildup, which violates the steady state assumption. So R6 and R4 are both clearly single essential. And so for R4 to be viable, we need both B and E to be produced. E can only be produced by direct import through R5. There's neither R1, R2, R3 can produce it, so R5 also becomes essential, while while B is only produced by R2. So R2 is also going to be single essential. Let's write this down for now. So we have R 4 is essential as it is the only reaction to produce D. R6 is essential to secrete D and allow production without violating steady state. R5 is essential as it is the only way to produce E, which is a necessary precursor to D. Similarly, R2 is similar in producing B. And lastly, we see that R2 requires metabolite A, which is only produced by R1, so R1 is also essential. In short, all reactions except R3 are essential. Because R3 produces C, which first of all not only does not lead into any production of D, but also doesn't get produced by anything. Not only is R3 not essential, but R3 cannot carry flux at all. So yeah, those are the essential reactions for this problem here. Next topic is epistasis. And so what do we mean by epistasis when discussing genetic interactions? So simply put, epistasis is when the expression of one gene alters the effect of another gene. So typically what that can mean is that you can have, say you have a gene mutation that would lead to a certain effect if it were to happen in isolation, but a secondary gene mutation either masks that original gene by producing another effect that is much more substantial. For instance, you can have a gene where the single knockout will grow at half the rate, but any case where you have but a second mutation which knocks the organism out entirely is going to essentially overwhelm and make the first mutation irrelevant. So how can we identify epistasis with double knockout analysis? Well, what we can do is we can first compute growth rates for single mutants in an organism. Then we can then compute all-to-all double knockouts in the same. And then essentially what we can do is we can compare the resulting growth rates for double mutants to the product of growth rates resulting relative growth rates relative to wild type to the product of growth rates for single mutants. So for instance, if mutant A has a growth rate of 0.7, and mutant B has a growth rate of 0.5, but mutant AB has a growth rate different to 0.35, we have epistasis. So the three types are buffering. The three types of epistatic phenotypes we can observe with double knockout analysis are buffering, where the effect of a second mutant of the double mutation is weaker than the product of each single mutant. For instance, growth rate mutant A is 0.5, growth rate mutant B equals 0.5, and growth rate AB also equals 0.5. This would be a case of buffer interaction. We have neutral, where growth rate A equals 0.5, growth rate B equals 0.5, and growth rate AB equals 0.25. This would be a case of neutral epistasis. And lastly, we have aggravating, where any individual mutation is reasonably limited in effect, but the combined mutation has a much greater one. So that would be, for instance, growth rate A equals 0.9, growth rate B equals 0.9, or even 1 for that matter, and growth rate AB equals 0.01. This would be a case of aggravating epistasis. So yeah, these are the three aspects of epistatic phenotypes we can observe through double knockout analysis. And our last question of this exam is on the topic of OpNock. So fundamentally, the purpose of OpNock is to engineer a cell to produce a desired metabolic byproduct. OpNock is usually used to optimize the production of a metabolic byproduct that we consider useful. And the base idea here is that the cell in any mutant it has will have its own objective function, which is growth, and it will adjust to that no matter what we do to it. What we want to do is we want to find a mutant where optimal growth involves production of the desired metabolite. We might imagine, for instance, the classical example of this would be something like brewing, where we're forcing a yeast cell into an anaerobic environment, because in order to grow in an anaerobic environment, it is forced to secrete alcohol. That is not something it will do in an aerobic environment, which would be more optimal for itself. It would be able to grow faster there. But if we force it to be anaerobic, the cell becomes forced to produce. Alcohol as a byproduct, because the only pathways it has that works for it in an anaerobic environment have alcohol or ethanol as a necessary byproduct. And OpNOC essentially does the same in terms of instead of forcing cell behavior through changing the nutrient environment, we're forcing cell behavior through genetic manipulation. So OpNOC, we search for mutants so that satisfaction of, or so that optimization of the cellular objective corresponds to an, or requires production of the desired metabolic byproduct. This can be viewed as reshaping the solution space so that the engineering objective and the cellular objective point in the same direction. Now, flux variability is useful when using OpNOC because for a given mutant, we might be able to identify a mutant which is capable of producing our engineering objective in the optimal state. But again, or in its optimal state in the mutant we find. But we will have no guarantee of that. In an FBA optimization, the cell only cares about its own objective. It doesn't care about ours. And so if we want to guarantee production of a byproduct, we need to perform FVA, because that will give us the lower bound of production of the engineering objective for that specific mutant in its own optimal, like in the optimal solution for that mutant. Since production of the metabolic of the engineering objective might be possible but not guaranteed for optimal growth in a given mutant, then we are at risk of finding mutants which will not behave as desired in practice. Using FVA to identify lower bounds for the engineering objective for a given mutant allows us to identify mutants with guaranteed yields of the engineering objective. And yeah, that's summary of the relationship between, or the necessity of including FVA when you're doing OpNOC. So yes, this is the end of last year's written exam, and I will later come out with the same, but for the computer lab exam, to see the kind of exercises that we had that can fall there, and the type of answers that I would like to give, or like a type of answers that yeah, I want.